Hello, welcome on behalf of TAS International. My name is Peter Rittmeyer. In this presentation we will start with the contact. After this introduction of the contact, there will be three other presentations which will deal with the three specific types of contact to be used within MADYMO. Those are the topics to be discussed in this introduction to contact. What is a contact? MADYMO geometrical entities, so the surfaces that make contact, the different types of contacts, and at the end we will get a table. This table I think is pretty useful to be used later on as well, because it gives you in a quick overview what type of contacts are available within MADYMO. Well, let me first start. What is a physical contact? Two geometrical entities are touching each other into space. There will be no penetration in neither one of them. The load transfer is done by material deformation. So the material is deforming and there is no contact. In MADYMO this will be slightly different in some of the contacts as you will experience. But first let me address the surface entities or the geometrical entities available within MADYMO to be defined for contacts. You probably already have seen them, the multi-body surfaces. Those can be either elliptical, planes or cylinders. Those are the three multi-body surfaces available for contact. Now we also have finite elements. Finite elements can be split up in facets and finite elements. Let me first start with the finite elements. Those are elements that are able to deform, and for that a material characteristic is required. Facets are a special type of finite elements. Some of the people or some of the users consider them as more advanced multi-body surfaces. I'll leave it up to you in which group you would like to place them. In this case they are put under the finite elements because they look more like finite elements, but facet elements can't be deformed. You have a finite element mesh which is fully supported on a rigid body, or even reference space if you like. The finite elements, those have material properties. The other, so the multi-body surfaces and the facets, require a contact characteristic because the deformation is not in a material model but is stored within the characteristic, and for that you will have large penetrations optionally within such types of contacts. It's not that the contact is failing, but it is because the deformation is stored into the contact. If you are going to look to your kinematics, that might look a bit strange, but there are many ways to check whether the results are as expected. Well, let me give a simple example. You see here two balls, a surface 1, let's call it the master surface, and a surface 2, let's call that the slave surface. The slave surface is moving in a downward direction, and for that is penetrating the master surface. It's an amount of lambda, and with this amount of lambda, the amount of penetration, a contact force is generated, which tries to push those two surfaces from each other again, such that the contact is released. Well, as said, the contact surface penetrating each other. It's for all type of contact available. However, the amount of penetration highly depends on the way you define your contact force. The dependency can be specified as a force penetration characteristic. That means if you apply a force at a certain amount of penetration, a force will be applied on the contact. This means, as it is a force penetration, that it is independent of the contact area or the thickness of the material itself. More advanced, but also more complex ones, are the stress relative penetration characteristics. Again, the deformation is stored inside the contact, the material deformation, and there is no material characteristic needed itself. That's different with respect to the adaptive penalty-based contacts. Those are real material-based contacts. They are only used for FE-FE contacts, so not with multi-body surfaces. In this case, you still have an amount of penetration, but that will be infinitely small. It's just, it needs to detect penetration, but the real deformation is handled by the material characteristic. Well, as said, there are three subclasses of contact. The first one is the contact MB-MB. It can be an ellipsoid, a plane or a cylinder, to an ellipsoid. The last ellipsoid in this case will be the slave surface. What the master and slave means will be explained in more detail later on. For this case, it's just good to know that you in principle have a master and a slave surface. There's one exception, and that's for the self-contact for an airbag. For contact MB-MB is a contact between an ellipsoid, a plane and a cylinder to a facet or to a deformable FE. And then the last one is a contact FE-FE. That can be either a contact between two facets, so for that you will need material contact characteristics. The deformation is handled by the contact, not by the material. The second one, a facet to deformable FE, or vice versa, is also an example of an FE-FE. That is a little bit more complicated, because there you also have the deformation of the FE mill itself. Or you can have a contact between a deformable FE and a deformable FE. Those are typically used for adaptive or penalty-based contacts. Now let's go to the last slide. Here you see a table with again the three subclasses MB-MB, MB-FE and FE-FE. On the vertical you see a difference between elastic and inelastic, and also characteristic based or material based. Let's first start with the first column, MB-MB. It's an MB-MB contact, so an ellipsoid, plane or a cylinder to an ellipsoid contact, and the only type available is a force penetration contact. So that means independent of the contact area. The second column, MB-FE, you have three options. Let me first address the elastic ones. There you have the possibility to choose between a force or a stress-based contact. Stress-based means that the contact area is taken into account. For the force-based, not. Then there is another type of contact, it's a kinematic contact. I recommend you to handle this with care. What it does is it allows no penetration. So at a certain moment a node is penetrating, and at the same moment it is pushed back to the surface. It can be applied sometimes, for example, between a dummy and the airbag, but take into account that in this situation the characteristics of the dummy, the material deformation which is stored in the contact characteristics, will not be taken into account. The last one is the FE-FE contact, and you have even four options. It can be a characteristic-based contact. Again, you have the possibility to choose between stress and forces, but now you also have the possibility to define a penalty or an adaptive. Adaptive, for example, is typically used for airbag self-contact or airbag to the IP or the windshield. It's a very robust contact, although it requires a smaller time step than the characteristic-based contacts. Penalty can also be used, but typically adaptive is preferred. That brings me to the end of this presentation. Goodbye.